Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on vectors. Now in particular in this presentation I'm going to introduce a way to multiply two vectors together called the dot product. Now in previous videos we've looked at how to add, subtract and scalar multiply with vectors, but this presentation is something new. How do we define the product or multiplication between two vectors? Now, the dot product, which I'm going to discuss with you today, is one way of defining multiplication, and we'll look at other ways in other videos. So I'm going to define the dot product of two vectors, and I'm going to discuss some examples. I'm going to show you some geometric interpretation as well between the angle between vectors, the lengths of those vectors, and the dot product. So let me share my screen with you and let's get underway. Okay, so what is the dot product? So I've already seen how to multiply a scalar or a number with a vector, but how can we multiply a vector with a vector? And what does it mean? And how would it be useful? So that's what we're going to discuss in this video. All right, so here is the definition of the so-called dot product in n-dimensional space. Let A and B be vectors. The dot product of A and B is defined as the following. You have this little dot between the two vectors, and it's basically just a multiplication between each of the corresponding components of each vector, and then you just sum all those together. So let me sort of break this down into 3 dimensions to give you a bit more definiteness here. So let's say we're working in R3. Okay, so in this case we have, say A might be a column vector with the components A1, A2, A3. The vector B might have, say, components B1, B2, and B3. So the dot product is the following. It's the first component multiplied with the first component plus the second component multiplied with the second component plus the third component multiplied by the third component. Okay, now that's still a little bit abstract, so let me just do an example and show you what it means for a specific A and B. So let's say A is the column vector 1, 2, 3, and let's say B is the column vector 7, negative 1, 2. Then A dotted with B, or the dot product of these two vectors, is just found by multiplying the corresponding components and adding everything together. Okay, so it's 1 times 7 plus 2 times negative 1 plus 3 times negative 2. 3 times 2. Okay, so we've got 7 minus 2 plus 6, which is going to be 11. All right, so the dot product of these two vectors is 11. Now let's just stop and think about the nature of this answer just for a second. The answer is a number. Okay, the answer is a number. It is not a vector. Okay, so note that our answer is a number, or a scalar if you like, and not a vector. Okay, so under this definition of multiplication, the dot product of two vectors, our answer will always be a number. It won't be a vector. Okay, so this kind of multiplication gives us a number as the answer every time. Okay. Now there are other ways of defining multiplication where you multiply the two vectors somehow and you get a vector as your answer. That'll be in other videos. All right, so the dot product always gives you a number as your answer or a scalar as your answer, not a vector. Okay, so that's just a little bit of algebra and defining this dot product. We can connect the dot product with lengths and angles via the cosine rule for triangles to obtain the following. And sometimes this is the form that you see in textbooks, for example, in engineering. This is how they define the dot product. Okay, so here the dot product is just the product of the lengths of the two vectors multiplied by cos theta, where theta is the angle between the vectors. So just to sort of remind ourselves, this notation is just symbolizes the length or magnitude of vector A, and the same with the other one. Okay, so the dot product, according to this, is the product of the lengths times the cosine of the angle between the two vectors. All right, so where does that come from? Well, I'm going to explain that in a little bit of detail, and it actually relies on, as I've mentioned up here, the cosine rule for triangles. Okay, all right, so let's talk about this a little bit more, and I'll see if I can actually prove this. Okay, so suppose I've got two vectors. Okay, say A and B. All right, and essentially what I want to come up with is this. So the dot product is equal to this. Okay, all right, there's an angle theta between them. And if I draw in a third vector, then I have a triangle. Okay, let's call that vector C. Okay, now by the cosine rule, I can relate the lengths of the three sides with the cosine of this angle. Okay, the cosine rule says the following. The length of this side squared is equal to the sum of the lengths of the other two sides. So it looks like Pythagoras' theorem here, but this isn't necessarily a right-angled triangle. So this extra term takes care of the non-right-angledness, if you like. Okay. Okay, so you'll notice that there's the product of these lengths and the cosine theta, and over here there's the product of these lengths times cosine theta. So what we're going to try to do is rearrange this and show that whatever's on the other side is just the dot product in this form. Okay, all right. So let's have a look at expressing the vector C in terms of the vector A and B. Now, by the triangle law of vector addition, we know that this vector A plus this vector B equals the vector C. Sorry, I beg your pardon. The vector A plus the vector C equals the vector B. Okay, so the vector A plus the vector C equals the vector B by the triangle law of addition. So if I isolate the C, okay, so if I rearrange this and make this the subject, Let's call this star. Let's write it down here. Okay, so I'm going to take this to the other side, take the c squared to the other side and divide by 2. I can replace this with that. Okay, so if I take the magnitude of that, or the lengths, I'll just get the following. Okay, and now I'm going to look and see what this reduces down to in the component form. Okay, so this is just the length of the vector A squared. Now I know from previous videos, let's say I'm working in three-dimensional space here, the length of a vector squared is just the sum of the squares of the components. Okay, so let's just work with 3 dimensions here. Same with this one. You square the components and you add them together. And what have we got here? Well, this is one vector taken away from the other vector, and you just square the length of that. So again, in a component-wise fashion, it would be B1 minus A1 all squared, plus B2 minus A2 all squared, plus B3 minus A3 all squared. Okay? All right, so now we're going to look for some cancellation. Okay, now I've got an A1 squared there and no other A1s except for what's in here. All right, now when I multiply, and if I expand this bracket, I'm going to get a positive A1 squared, and it's going to be negative. So that A1 squared and the A1 squared in there is going to cancel out. The same with the A2 squareds, the same with the A3 squareds, the same with the B1 squareds, B2 squareds, B3 squareds. Okay, so a lot of cancellation goes on. The only terms that are not going to cancel are when you multiply these two together. Okay, so when you multiply these two together and multiply by 2, you're going to get negative 2 A1 B1. You've got a negative sign there. So it's going to be 2 A1 B1. Same with this one. And the same with this one. Starting to look familiar? It's starting to look a lot like this now. Okay, in fact, if I take out the 2, it's just the following, which is how we defined the dot product of A and B. Okay, so this, the length, the product of the length times cosine theta, where theta is the angle between A and B and theta is between 0 and pi, is equal to the dot product, at least in 2 and 3 dimensions. Okay, so we finished. All right, so that's where this comes from. In some books, this is just presented and saying, oh yeah, that's just how we're going to work with the dot product. Well, now you know where it comes from. Okay. So I'm going to do an example in a minute, but let me just go back here just for a second. I haven't talked about this yet. This proof works in 2 and 3 dimensions, but for dimensions higher than 3, we can actually use this to define what we mean by an angle between 2 vectors. Okay? So this then actually gives us a way of defining an angle between 2 vectors in higher dimensions. All right. Now, some of you are thinking, well, okay, so what's the point? What's the point? Well, there are 2 reasons why the dot product is important, and I'll discuss these in later videos. first of all is to compute the angle between vectors, and that has all sorts of nice applications. Okay, and secondly, to calculate the projection of one vector on another. Okay, and these ideas will be discussed in forthcoming videos. So we are going somewhere with this, but I wanted to discuss an example to really drive home the ideas and some of the calculations involved with this dot product. Okay, so we've got two vectors in three-dimensional space. Okay, we're asked to calculate the dot product of A with B, and we're also asked to calculate the angle theta between the two vectors. Okay, so first off, I'm just going to use this definition to compute the dot product, and in the second part I'm going to use this relationship here to calculate the, or this one here if you like, to calculate the angle between the two vectors. Okay, so let's run through it and see what we get. Okay, so the dot product of A and B is just multiplying the respective components with each other and adding them all together. So that with that, plus that with that, plus that times that. Okay, so that's going to be 0, that's going to be 0, and that's going to be 1 on root 2. All right, so that's pretty easy. And now let's calculate the angle between the two vectors. Now, to do that, we've already got the dot product. Let's calculate the magnitude or the lengths of each of the given vectors. Okay, and then we'll apply the formula. All right, so remember to calculate the length or the magnitude of a vector. You take the components, you square them, you add them together, and then you take the square root. Okay, so that's just Pythagoras' theorem at work. All right, so here we're going to have a half plus 0 plus a half. So I'm taking the square root of 1, positive square root, which is just 1. Let's compute the length or the magnitude of B, same thing. Square all of the components, add them together and take the square root. Okay, so that's going to be 1 plus 0, which is 2, take the square root. So we can now apply this formula here to calculate the cosine of the angle, from which we'll be able to compute the angle theta. All right, so the dot product is 1 on root 2, and the product of the length is just 1 times root 2. So if I clean that up, I'll get 1/2. So I know the cosine of the angle between the two vectors A and B is 1/2. Okay, so how do I know what theta is? Well, you can, work it out. You can either do it using a triangle, or you can just, you may just know that off by heart. So, okay, if you say draw a little triangle in, okay, this isn't to scale. Okay, this angle is going to be pi on 6. This angle is going to be pi on 3. This is a right angle. So cosine is adjacent over hypotenuse. So if I choose this angle here, adjacent over hypotenuse will give me 1 on 2. So theta equals this angle in here, pi on 3. Okay, so the dot product of these two vectors is 1 on root 2, and the angle between them is pi on 3. Okay, so that's a little bit about the dot product. In other videos, I'll be talking a little bit more about the dot product and its applications to the ideas that I mentioned, like projection and more about angles, orthogonality of vectors. You might have heard of that. So we're going to go with this in a few interesting directions, and I hope you can join me for forthcoming presentations where I'll continue my series of videos on vectors. If you have any comments, questions, put them in the comment section. Thanks again for watching. Bye.